Alrighty, here is a quick little video for section 3 in chapter 17. Today, or in this video, we're going to talk about cell potential, electrical work, and free energy. I will attempt to keep this as short as possible. However, the last problem on the fourth slide is pretty lengthy, so don't be surprised if we spend a lot of time on that slide itself. So let's get started here. Cell potential, electrical force, and free energy. The relationship between thermodynamics and electrochemistry is that the EMF, the electromotive force, is equal to the potential difference in voltage, which is equal to the work in joules divided by the charge in coulombs. Now, you might remember when we talked about, in section 2, we talked about a coulomb, and I said, well, that's coming later. Well, here it is. So what does this mean? It means that a joule of work is produced when 1 coulomb of charge is transferred between 2 points in the circuit that differ by a potential of 1 volt. Now you might be asking yourself, what the heck is a coulomb? That's coming on the next page here. But work is viewed from the point of view of the system itself. Thus, the cell potential and work have opposite signs. So E is equal to negative W over little q. Or you could say negative W equals E times Q. If we look on the next page, then it says, what do all these letters mean? Well, in this case, that little q, now remember we talked about heat before with a little q? Now little q means a quantity of charge in coulombs transferred. And so now we're going to get into what is a coulomb. Well, we have a number called a Faraday, an F, capital F. The charge on 1 mole of electrons is 96,485 coulombs of charge. So now that kind of tells you what a coulomb is. It's a unit of charge. 96,485 of these units of charge equals a Faraday. And we can make this equivalent statement here that Q is equal times the number of moles of electrons times a Faraday, 96,485 coulombs per mole electron. So Q is really coulombs. I know, a little weird. So for a galvanic cell, the work maximum is equal to delta G, or the free energy. Or this equation, which you'll find on your sheet from AP, that delta G equals negative N. Whoops, that's an N, not an M. N times capital F, which is that Faraday, times the potential. Or the standard free energy, remember that little zero means standard, is equal to negative N times a Faraday times the standard electrical potential. So this equation states that the maximum cell potential is directly related to the free energy difference between the reactants and the products in a cell. So let's take a look at the next slide. It says, using the data in the table in the book, calculate delta G0 for the reaction, and you need the reaction, Cu plus 2 plus Fe gives you Cu plus Fe plus 2 charge. Is this reaction spontaneous? Well, let's take a look at the half reactions. We have one half reaction where Cu plus 2 electrons gives us Cu. Now you have to ask yourself, is this oxidation or is this reduction? Well, we know it's reduction because we are gaining electrons. The electrons show up on the reactant side. So if we look on our data table in that book that I showed you, you get 0.34 volts. Now, that's reduction. Here's our oxidation reaction. That has to be Fe, goes to Fe plus 2 electrons. And if you look again on that table in the book, you would actually get negative 0.44 volts. But because we are flipping it to be an oxidation reaction, it becomes positive 0.44 volts. So the E of the cell is going to be adding them together, 0.34 plus 0.44 equals 0.78 volts. All right, so now that we have the E of the cell, I suppose we should call that E0 of the cell. We could calculate delta G0 of the cell. So delta G equals negative N F E of the cell. Now the question becomes, what do we put in there for this N value. N is the number of moles of electrons that are being transferred. So we go back up to our equations. 2 electrons, 2 electrons. That means that there are 2 moles of electrons that are being transferred. So our N value is going to be 2. Faraday's constant is a constant, so it's 96,485 coulombs per mole of electron. This is 2 moles of electrons, so you can see how that cancels out so that coulombs remains there. And we know that our potential of the cell is 0.78 joules per coulomb. So now here this C is coulomb instead of C as in Celsius. So what does this equal? This equals negative 1.5 times 10 to the 5th joules. This negative sign for the delta G means that it's a spontaneous reaction. So because the potential of the cell is positive and delta G is negative, we know that this is spontaneous. Now, I know that was really quick, but if you need to go back and look through it again, this example is in your book. You can also go back and kind of pause so that you can prove to yourself that each of the steps that I did were true to the point where you can understand it. So let's take a look at the example. Now, this is the one that we're going to spend a little bit of time on. The example here, and now I lost my page in the book. But the example here talks about using the data in the book, predict whether a 1 molar HNO3 will dissolve gold metal to form 1 molar Au plus 3. So Au plus 3 being gold ions in solution. So if we take a look, we need to come up with our own kind of equation for this. And this becomes a little messy. So how would you go about doing this? Well, you would have to find something on that page in the book that would give you a half reaction that includes nitric acid, the HNO3, and includes gold, the Au to the Au plus 3. And then you have to determine what's the anode, what's the cathode. So here is one of the half reactions that you would do if you went and looked in the book at that chart with the standard reduction potentials. You would find that NO3 minus plus 4 H pluses plus 3 electrons gives us NO plus 2 H2O. And you would find that the E of the reaction would be 0.96 volts. Then you would find that the gold creates gold ions plus 3 electrons, and it's at 1.5 volts. But because we reverse the reaction to make it oxidation instead of reduction, we need to add a negative sign in front of it. So again, take the time to go back to that page. Let me just check what page it's on again. Page 796. Take your time, go back to page 796 to prove that these two reactions make sense and that when you add them together, you would get HNO3 dissolving Au plus, or Au to get Au plus 3. So the E of the cell here would equal 0.96 plus 1.5, plus a negative 1.5, which would give us a negative 0.54 volts. So our E of the cell is negative. So it is not going to be spontaneous. And if you were to feed this into the equation of delta G0 equals negative NF E cell, you would find that we would have 3 electrons. We would have Faraday's constant. And then we would have this negative 0.54 volts. These negatives would cancel out, giving us a positive delta G, meaning that it is not spontaneous. So 2 different ways there that you can prove that it's not spontaneous. So that's the gist of section 3, which talks about free energy and how you can relate cell potentials to free energy to prove whether or not a galvanic cell will be a spontaneously occurring reaction or not. So what did this last one really tell us? It told us that some reactions just won't happen, and it's because they don't have the potential to happen. And because they electrically will not occur, the free energy will be positive, meaning that it's going to be a non-spontaneous reaction.